Hello students, so today I am going to show you few more examples of lesson moment of force. We have already done first video where we have discussed basic numericals which are related to moment of force. Today we will go little further. Let us begin with the first numerical for today's video. It is the seventh sum from your textbook. A steering wheel of diameter 0.5 meter is rotated anti-clockwise by applying two forces, each of magnitude 5 Newton. Draw a diagram to show the application of forces and calculate the moment of forces applied. My dear kids, do you remember our concept of couple? What was couple we discussed in the first video? Two forces equal in magnitude, opposite and parallel to each other. You all might have seen how do we hold the steering wheel. You must have seen how does driver holds it, right? Like this, isn't it? With these two hands. And then he is doing this action. So there are two forces acting on the steering wheel. And steering wheel has got circular shape. So, distance between these two forces will be the diameter of the steering wheel. In these two hands, I have got a steering wheel. Distance between these two forces will be nothing but the diameter of the steering wheel. Okay, let us see the diagram. Okay, given diameter of the wheel 0.5 meters, which is given to us. Each force is of 5 Newton. We have discussed. In couple, both the forces are equal in magnitude. So, magnitude of forces 5 Newton. Fine. Now, see this figure. Just now I told you. Here we have steering wheel whose diameter is 0.5 meter and two forces of equal magnitude 5 Newton that is applied on the steering wheel. And I told you these are two forces. For example, with this particular hand, if I am doing this action, with this hand, I'll do this action. Then only steering wheel will be rotated, right? So, this force is in this direction and this force is in this direction. So, they are in the opposite direction. And hence, we have drawn these 5 Newton forces in the opposite direction. And hence, again, I'm repeating, it is the example of couple, right? Let's move ahead to find moment of forces applied. Moment of couple, moment of forces, that means moment of couple. This you need to understand, okay? In the question, it is not mentioned, but we have to understand the concept of couple, which is to be applied over here. Formula, moment of couple is equal to either force into couple arm. Please refer to our first video for this particular formula. Moment of couple is equal to either force, which is 5 Newton, and distance between both the forces, that is nothing but couple arm, which is nothing but the diameter of the wheel, 0.5 meter, and thus we get the answer 5 into 0.5, 2.5 Newton meter. Thus, the moment of couple is 2.5 Newton meter. It's very simple. So, this is the example based on the concept of couple. Let us move ahead to check one more concept. Let us see. A uniform meter rule. Meter rule is your ruler scale. A uniform meter rule is pivoted at its midpoint. Pivoted, that is a fixed point. We all know the word pivot, fulcrum. So, this ruler is pivoted at midpoint. A meter rule. Meter rule means what? The length of the entire meter rule is 1 meter. 1 meter is equal to 100 centimeter. And at the midpoint of this ruler, pivot is fixed. And what is the midpoint? 50 centimeters, obviously. A weight of 50 GF is suspended at one end of it. So at the one end of the meter rule, 50 GF weight is hanging. Suspended means it is hanging. And I think you all have studied in your theory, GF is the unit of force, gravitational unit of force. So in your numericals, normally you all will come across with GF and KGF in this chapter. So please keep it in mind, every time Newton will not be there. So you have to check what is the unit of weight or what is the unit of force is given to you in the numerical, and you have to follow the same system while solving. So a weight of 50 GF is suspended at one end of it. Where should a weight of 100 GF be suspended to keep the rule horizontal? Very important word. To keep the rule horizontal, we have discussed in our first video that to keep this ruler horizontal means in equilibrium. So this particular problem is based on concept of equilibrium. Try to recollect that concept. So we have to keep the ruler in equilibrium, and whenever any body is in equilibrium which is fixed at one particular point, we use the concept of anti-clockwise moment is equal to clockwise moment. Then and then only this meter rule will be remaining in horizontal way. Let's move ahead. So see this figure. This is the figure of ruler. AB is your meter rule, which is of length 100 centimeter, and the pivot is at 50 centimeter, that is at its midpoint, which is given to us. They have also said in the problem, a weight of 50 GF is suspended at one end. So we have considered at end A, we have suspended 50 GF. 50 GF will cause this kind of moment. Now this kind of moment is which kind of moment? It is the anti-clockwise moment. This 50 GF will try to pull this meter ruler in anti-clockwise direction. If I have to keep this meter ruler in horizontal plane or in equilibrium, I must have some other weight to balance this, to balance anti-clockwise and clockwise moment. So they are talking about 100 GF weight. They have given us weight that you have to suspend 100 GF weight. But exactly where? Here, where? That we need to find out. You can see here 100 GF, where to place, right? So that is our numerical कि कहाँ इसको रखना है, right? Fine. Let us move ahead. Given length of meter scale 1 meter, weight W1 is 50 GF. Distance D1 from one end is 50 centimeter. This distance, because whenever we calculate moment of force, because the lesson itself depends upon moment of force, we all know that we need to find out the distance between the line of action of force and pivot. That is a fixed point. So this distance is 50 centimeter. This weight is been given to us, that is 100 GF. But we do not know exactly at what distance it should be placed. That is our main objective to solve this problem. Weight W2 is 100 GF. To find distance of the weight 100 GF from the pivot. Formula which we will be using, basic formulas, of course, moment of force equal to force into distance. Let's move ahead. Now, how are we going to solve this? I told you this is the problem based on equilibrium. So, anti-clockwise moment is equal to clockwise moment. This is the basic formula which we need to use it. Let D2, this distance, D2 be the distance of 100 GF weight from the pivot, right? So, we are aware of this weight, this distance, this weight, but we don't know distance D2, which we need to find out. So from the principle of equilibrium, my dear students, many times it is found children simply write the formula, but they do not write anything about word equilibrium. So whenever you are going to use the formula, please mention it is according to the principle of equilibrium anti-clockwise moment equal to clockwise moment. Now, anti-clockwise moment will be how much? The force, that is weight W1 into distance D1, and clockwise moment is due to this weight W2 into this distance D2. Let us substitute 50 into 50 centimeters equal to W2 is 100 into D2. After calculation, D2 equal to, keep this D2 over here and shift this 100 here, 50 into 50 upon 100 equal to D2. So, after calculation we get 25 centimeters from the pivot. So, this distance comes to 25 centimeters from the pivot. Okay. So, what is asked? Where should a weight of 100 GF be suspended to keep the rule horizontal? So, one can answer this in this way, that 100 GF can be placed at 25 centimeters from the pivot. Somebody may say 100 GF weight can be placed at 25 centimeter from the other end, because the entire distance is 50 centimeter. So, this is 25. So, the remaining distance would also be 25. So, thus we say either 25 centimeter from the pivot, or you can say 25 centimeter from the other end. So, the weight should be suspended 25 centimeters from other end. Now, let us see the next sum, again based on concept of equilibrium. Little bit difficult. Everything is easy. You have to only think and you have to use your theory. Let us see. A uniform half meter rule can be balanced at 29 centimeter mark when a mass 20 grams is hung from its one end. A uniform meter rule? No, it is half meter rule. Very important word. Half meter rule means its length will be only 50 centimeters. Entire meter rule has 100 centimeter length. Half meter rule will have 50 centimeter length. Now, this half meter rule is placed at 29 centimeter, not at 25, 29. But when is it possible to balance this meter rule? When it is placed at 29 centimeter and at one end 20 gram is hung. Then only it is remaining in the balance condition or in equilibrium. What is the question? Draw a diagram of the arrangement. Find mass of the half meter scale. In which direction would be balancing point shift if 20 grams mass is shifted inside from its one end? It may sound little bit difficult. No issues. We'll see one by one. Okay. Let us see. Solution. A diagram of arrangement. Now, how one has to draw the diagram? Let us find it. See, this is half meter scale, that is 0 to 50 centimeter, half meter scale. Now, actually speaking, 25 centimeter is its midpoint. But this meter rule is balanced at 29 centimeter. So, our pivot has to be at 29 centimeter. Fine? Okay. And at one end, 20 grams is hung. Now, you might be wondering why we have put this arrow showing some weight at 25 centimeter. Students, you have to think from one more concept, that is center of gravity. It is in your B part of the lesson. Center of gravity. I'm not going to teach you center of gravity right now because this video belongs to the numericals. But in short, I will let you know. Center of gravity is that point in the body where the mass of the entire body is concentrated. Means it is the point, say 25 centimeters, the midpoint of this half meter scale. So, we know the midpoint of the meter scale or midpoint for any rod becomes its center of gravity. So, at 25 centimeter, the weight of entire meter scale will act. Center of gravity is that point at which the weight of entire object, entire body will act. So, this W stands for the weight of entire half meter scale. So, at 25 centimeter, we are showing one more W, that is this weight of meter scale is acting in the downward direction. So, see in this figure, there are two weights. One which we have hung at one end, that is at 50 centimeters, and another which we have not actually done anything, but it is there, that is at the center of gravity at 25 centimeter, weight of the entire meter scale is acting. So my dear kids, actually this weight over here is causing anti-clockwise moment, and this anti-clockwise moment is balanced by clockwise moment produced by 20 GF weight. So though this is not actually visible to us, but it is there. So my dear students, please keep it in mind whenever such numerical comes where meter scale is pivoted at other than its midpoint. I repeat, when meter scale is pivoted at a point other than midpoint, then you need to consider at its midpoint, its center of gravity lies where weight of entire meter scale acts in the downward direction. Very important concept on which this entire sum is based. So this is the diagram. Now let us see further. If WGF is the weight of half meter rule, this is the W, fine. Then by the principle of moments, where we need to use it in equilibrium, what have we said? W into D1, we know it, W1 into D1 equal to W2 into D2. We all know it. Now, how much is the weight of the meter scale? We don't know, but this weight is causing anti-clockwise moment is equal to, this is your clockwise moment, isn't it? Now, this is W into distance D1. Now, what is this distance? This distance is from the pivot. Pivot is over here at 29 centimeter and this center of gravity lies at 25 centimeter. So, distance between this point and this point, distance between 29 and 25 is the distance which is to be considered, because we have studied according to the moment of force. Which distance do we consider? Perpendicular distance between the line of action of force and the pivot. So, it is this distance from 25 to 29. Hence, we have written 29 minus 25 is equal to, see the other side. This is your weight 20 GF and distance between line of action of force and fulcrum, that is, it is from 29 to 50. So, 50 minus 29 will be the distance. Going ahead, so W equal to 4 equal to 20 into 21. Just subtract and you get the answer. So, W equal to, take this 4 down, 20 into 21 upon 4, and after calculation, what you get is 5 into 21, that is 105 GF. Now here it is W. W is weight. Weight is always in GF, 105 GF. But what is asked? Find mass of the half meter scale. And we all know mass is calculated in kilograms and grams. I cannot write कि mass of meter scale is 105 GF. I would have written weight of meter scale is 105 GF. But ask mass. So, mass of the meter scale becomes 105 grams. Very important concept. Please do this sum 2 times in your notebook. Let us see the C part of this sum. I am reading the C part. In which direction would the balancing point is this, that is your fulcrum. In which direction would the balancing point shift if 20 grams mass is shifted inside from its one end. Right now 20 GF is at the end. If at all I have to shift 20 GF inside, what would happen to this fulcrum where it should be shifted so that meter scale remains in equilibrium? Let us see that. 20 GF has to be shifted inside. Now what have we written? When 20 gram mass is shifted. Now see children, over here also what have we written? Mass, if I'm using the word mass, it should be 20 G, not GF. When 20 GF mass is shifted inside from its one end, the force remains the same. Have we changed this 20 GF? No. Weight, force, that is remaining same. That is 20 GF. But what is happening to the distance? See, if it comes inside, distance between the fulcrum and 20 GF will decrease. Then, the perpendicular distance of the mass from the pivot will decrease. It was 21, 29 to 50, it was 21. If it is brought inside, obviously distance will decrease and then the scale will no longer remain in the equilibrium, isn't it? It will start moving. It will not be in the equilibrium. Then what should be done? If this distance is getting decreased, so in order to bring the rule at the equilibrium, the balancing point will be shifted towards the 25 centimeter mark. See, if this is coming inside, distance will decrease. And for balancing, that distance has to be more. So obviously, this point has to go towards 25 centimeter, then and then only balancing would be possible. I'm repeating, if this weight comes inside, this distance will decrease. So in order to keep the meter rule in balance position, this fulcrum has to be shifted more towards 25 centimeters. So that is how this problem is to be solved. This problem is the representative problem for many more problems of your textbook. So once you do this problem thoroughly by a proper understanding, all other problems would be easy.